We have already discussed Kirchhoff's voltage law. Let us discuss it once again in detail. This law states that sum of the voltage rises in a loop is always equal to sum of the voltage drops. We consider a simple series circuit as shown in figure number 1.15. We have applied a DC voltage source across the series combination of these three resistors R1, R2 and R3. There will be a DC current in the circuit which is represented by capital I. The DC current in the resistor R1 results in a voltage drop across the resistor R1 which is represented by V1. This current results in a voltage drop across R2 which is represented by V2. The same current represents a voltage drop across the resistor R3 that is represented by R3. So we have applied a DC voltage across the series combination of three resistors. There is a DC current in the clockwise direction in this loop. The voltage drop across the resistor R1 is V1. The voltage drop across the resistor R2 is V2. The voltage drop across the resistor R3 is V3. You see the current in this loop is in the clockwise direction, and we apply KVL to this loop. According to KVL, the sum of the voltage rises will be equal to sum of the voltage drop. So KVL states that sum of the voltage rises in a loop will be equal to sum of voltage drops. This is the statement of KVL. So keeping in view the direction of the current in this loop, the voltage across the source is a voltage rise. Why? Because the current flows from the negative terminal of the source towards the positive terminal. The voltage across the resistor R1 is a voltage drop. The voltage across resistor R2 is a voltage drop, and the voltage across resistor R3 is a voltage drop. So according to KVL, the sum of the voltage rises in this loop will be equal to the sum of the voltage drops. So Vs will be equal to V1 plus V2 plus V3. We can write down this equation in this format as well. We have Vs minus V1 minus V2 minus V3, which is equal to 0. So we can write down the first equation of this particular slide in the form of second equation. And this equation states that the algebraic sum of all the voltages in a loop is always equal to 0. This is another statement of KVL. What is another statement of KVL? That the algebraic sum of all the voltages in a loop is always equal to 0. What we do in this algebraic sum, we place a plus sign with all the voltage rises, and a minus sign with all the voltage drops, and then we add them. So this summation will result in 0. Anyhow, we consider equation number 1 over here. Now we calculate V1. The voltage drop across R1 will be equal to IR1. Similarly, the voltage drop across R2 will be equal to IR2. The voltage drop across R3 will be equal to IR3. So we put the values of V1, V2 and V3 in equation number 1. What is equation number 1? Let me write down equation number 1 over here. Vs, which is the voltage rise in the loop, is equal to V1 plus V2 plus V3. This is equation number 1. So we put the values of V1, V2 and V3 in equation number 1. After putting the values and rearranging the values, equation number 1 can be written as this Vs will be equal to I into R1 plus R2 plus R3. Let's say this equation is equation number 2. This is equation number 2. Okay. Now what we do, we replace the series combination of R1, R2 and R3 by a single resistor. The resistance of the single resistance is represented by RT. We assume that the resistance of the single resistor is equal to the total resistance of the series circuit. So what we do, we replace the series combination of R1, R2 and R3 by a single resistor, and we assume that the resistance of this single resistor is equal to the total resistance of the series circuit. And there are 3 resistors in the series circuit, R1, R2 and R3. We apply the same voltage across this single resistor. The same DC current flows in this resistor as well. There is no difference between the DC current of circuit number 1 and the DC current of circuit number 2. This current results in a voltage drop across this resistor, which is represented by Vt. So we apply KVL to this loop. According to KVL, the sum of the voltage rises in this loop will be equal to the sum of the voltage drop. Keeping in view the direction of the loop current in this circuit, the voltage across the source is a voltage rise and the voltage across the resistor is a voltage drop. We know that the voltage drop across the single resistor in the second circuit will be equal to IRT. As RS is as Vs is equal to Vt, so we can replace Vt in equation number 42 by Vs. Now we compare equation number 43 with this particular equation, which was our equation number 2. We know that Vs will be equal to I into R1 plus R2 plus R plus R3. This was equation number 2. We compare this equation with equation number 43. If we compare these two equations, the total resistance of the series combination will be equal to R1 plus R2 plus R3. So this will be the total resistance of the series combination. We consider this series circuit once again. There is an active circuit element in this series circuit, which is the voltage source, and there are three passive circuit elements in this series circuit: the resistor R1, the resistor R2, and the resistor R3. This passive circuit element will deliver energy to these three passive circuit elements. So the source deliver energy and these three passive circuit element take energy from the voltage source. So according to the law of conservation of energy, the power supplied by the voltage source will be equal to the power taken by the entire circuit. We can calculate the power supplied by the voltage source with the help of this equation. The power supplied by the voltage source will be equal to Vsi, that is the voltage across the source multiplied by the current in the source. The power consumed by R1 will be equal to I square R1. The power consumed by R2 will be equal to I square R2, and the power consumed by R3 will be equal to I square R3. So the total power which is consumed by the entire circuit will be equal to P1 plus P2 plus P3. So this will be the total power which is consumed by the entire circuit. We do a numerical question, which is a solved numerical question from my personal book. Consider the series circuit as shown in figure number 1.17. The DC voltage across this series combination is 10 volt. So the DC voltage across this series combination is 10 volt. Find the current, the voltage drop across each resistor, and the power consumed by the entire circuit. So we have got R1 of 2 ohm, R2 of 3 ohm, and R3 of 5 ohm. We need to calculate the DC current in this series circuit, the voltage drop across each resistor. It means that we need to calculate V1, V2, and V3. and the power consumed by the entire circuit. Well, we know that the applied voltage in accordance with KVL will be equal to I into R1 plus R2 plus R3. We discussed this equation in the theory 2 minutes ago. So the source voltage will be equal to I into R1 plus R2 plus R3. So the total current in the circuit will be equal to Vs divided by R1 plus R2 plus R3. Vs is 10 volt and the total resistance of this series combination is 10. So there will be a current of 1 ampere in this series combination. The voltage drop across R1 is V1 and V1 will be equal to IR1. So the voltage drop across R1 is 2 volt. The voltage drop across R2 is equal to V2 and V2 is equal to IR2. So the voltage drop across R2 is 3 volt. The voltage drop across R3 is V3. V3 will be equal to IR3. So the voltage drop across R3 is 5 volt. The power supplied by the voltage source will be equal to VSI. So the voltage across the source is 10 volt and the current in the entire circuit is 1 ampere. So the power supplies, the source supplies a power of 10 watt. And according to the law of conservation of energy, the power supplied by the voltage source will be equal to the power taken by the entire circuit. So the power supplied by the voltage source will be equal to the power taken by the entire circuit. So the power taken by the entire circuit will be 10 watt. We consider capacitors in a series circuit. We consider 3 capacitors in this series circuit. The capacitance C1, the capacitor C2 and the capacitor C3. We apply a time varying voltage across the series combination of these 3 capacitors. There will be a time varying current in this series combination, and this time varying current results in a voltage drop across C1, which is V1, a voltage drop across C2, which is V2, and a voltage drop across C3, which is V3. So we apply KVL to this loop. According to KVL, the sum of the voltage rises in this loop will be equal to the sum of the voltage drops. So the voltage across the source is a voltage rise, V1 is a voltage drop, V2 is a voltage drop, and V3 is a voltage drop. So Vs will be equal to V1 plus V2 plus V3. This equation, the first equation, can be written as Vs plus minus V1 plus minus V2 plus minus V3 will be equal to 0. So this means that the algebraic sum of all the voltages in this series circuit will be equal to 0. What we do in this algebraic sum, we place plus sign with all the voltage rises and minus signs with all the voltage drops, and we add them. So the addition results in 0. So the algebraic sum of all the voltage in a loop is always equal to 0. The voltage drop across C1 is V1, and V1 will be equal to 1 over C1 into the integral of I dt. The voltage across the capacitor C2 will be equal to 1 over C2 into the integration of I dt. The voltage across C3 will be equal to V3, and V3 will be equal to 1 over C3 into the integration of I dt. We put the values of V1, V2 and V3 in this particular equation. You know that the voltage across the source is equal to V1 plus V2 plus V3. So we put the values of V1, V2 and V3 in this equation, and we rearrange the right hand side of this particular equation. So we put the values of V1, V2 and V3 in that particular equation. So if we put it in that particular equation, the voltage across the source will be equal to 1 over C1 into the integration of I dt plus 1 over C2 into the integration of I dt plus 1 over C3 into the integration of I dt. Then we rearrange this particular equation. So if we rearrange this particular equation, the source voltage will be equal to 1 over C1 plus 1 over C2 plus 1 over C3 into the integration of I dt. Let me call it equation number A. Now what we do, we replace the series combination of C1, C2 and C3 by a single capacitor, and we assume that the capacitance of this single capacitor is equal to the total capacitance of the series combination. You see, there are three capacitors in our series combination, C1, C2 and C3. So over here we assume that the capacitance of this single capacitor is equal to the total capacitance of our series circuit. So the series circuit is circuit number 1 and this circuit is circuit number 2. So we apply the same voltage across this single capacitor. There will be the same current in this single capacitor. I mean, there will be no difference in the current of circuit number 1 and this particular circuit. This is circuit number 2. So this current results in a voltage drop across the single capacitor. We apply KVL to this particular loop. According to KVL, the sum of the voltage rises will be equal to the sum of the voltage drop. So Vs is equal to Vt. We apply KVL to this loop. According to KVL, the sum of the voltage rises in this loop will be equal to the sum of the voltage drops. Keeping in view the direction of the current in this loop, the voltage across the source is a voltage rise and the voltage across the single capacitor is a voltage drop. So Vs will be equal to Vt. Vs will be equal to Vt, and the voltage across the capacitor will be equal to 1 over Ct into the integration of I dt, and we know that Vt is also equal to Vs. So Vs or Vt will be equal to 1 over Ct into the integration of I dt. This is equation number B. We compare equation number B with equation number 1. Where is equation number 1? Let me show you equation number 1. Equation number A. So this is equation number A. So we compare equation number B with equation number A. If we compare equation number A with equation number B, we obtain the total capacitance of this series combination. We can calculate the total capacitance of this series combination with the help of equation number 54. So 1 over Ct will be equal to 1 over C1 plus 1 over C2 plus 1 over C3. We can calculate the total capacitance with the help of this particular equation. Kirchhoff's current law. We consider a parallel circuit over here. There are 3 resistors in parallel. We apply a DC voltage across the parallel combination of R1, R2 and R3. We apply a DC voltage across the parallel combination of R1, R2 and R3. The total current in this parallel combination is represented by Is. There is a single node in the entire circuit, which is shaded over here. So the total current divides into 3 parts at the given junction at the given node. The current in the resistor R1 is I1. The current in the resistor I2 is the current in the resistor R2 is I2, and the current in the resistor R3 is I3. The voltage across the resistor R1 is V1. The voltage across the resistor R2 is V2. The voltage across the resistor R3 is V3. As all these circuit elements are in parallel, so the same voltage will appear across all these circuit elements. So it means that the voltage across the source will be equal to the voltage across R1, and the voltage across R1 will be equal to the voltage across R2, and the voltage across R2 will be equal to the voltage across R3. So V1 will be equal to V2 and it will be equal to V3. KCL states that the sum of the currents moving towards the node will be equal to sum of the currents moving away from the node. So there is only one current which is moving towards the node. This current is Is. There are 3 currents which are moving away from the node: the current I1, I2 and the current I3. So the total current according to KCL will be equal to I1 plus I2 plus I3. We can calculate I1 with the help of this particular equation. The voltage across R1 divided by the resistance R1 will give you the current I1. We know that the voltage drop across the resistor R2 will be equal to I2 R2. So I2 will be equal to V2 divided by R2 or Vs divided by R2, we know that Vs in this particular case is equal to V2. So the current I2 will be equal to V2 by R2 or Vs by R2. The voltage drop across the resistor R3 is I3R3. So I3 will be equal to Vs by R3 or V3 by R3. We know that V3 is equal to Vs. We put the values of I1, I2 and I3 in this particular equation. We know that the total current in this parallel combination is equal to I1 plus I2 plus I3. So we put the values of I1, I2 and I3 in this particular equation. If we put the values of I1, I2 and I3 in this particular equation, we obtain this particular equation. This total current will be equal to Vs into 1 over R1 plus 1 over R2 plus 1 over R3. Now what we do, we replace the parallel combination of R1, R2 and R3 by a single resistor which is represented by RT. We replace the parallel combination of R1, R2 and R3 with a single resistor. And we assume that the resistance of the single resistor is equal to the total resistance of the parallel circuit. So the parallel circuit is your circuit number 1 and this equivalent circuit is your circuit number 2. So we apply the same voltage across this single resistor as well. So the same voltage is applied across the single resistor. The same current flows in the single resistor over here. I mean, there is no difference between the total current of the parallel circuit and the current of this circuit number 2. This current will result in a voltage drop across this single resistor, which is Vt. We apply KVL to this particular circuit or this particular loop. According to KVL, the sum of the voltage rises in this loop will be equal to the sum of the voltage drop. And the voltage drop, which is equal to the voltage rise, will be equal to IRT. This will be the voltage drop across the single resistor, and we can calculate Is from this equation. So the current in circuit number 2 will be equal to Vs divided by RT. So we compare this equation with another equation. We obtained this equation as well. Is, the total current, is equal to Vs divided by R1 plus R2 plus R3, and we compare this equation with this equation. So we derived this particular equation. If we compare these two equations, you see the total resistance of the parallel combination will be equal to 1 over R1 plus 1 over R2 plus 1 over R3. So we can calculate the total resistance of the parallel combination with the help of this particular equation. So 1 over RT will be equal to 1 over R1 plus 1 over R2 plus 1 over R3. We consider this parallel circuit once again. There is an active circuit element in the entire circuit, which is the voltage source, and we know that the voltage source delivers energy to the entire circuit. There are three passive circuit elements in this parallel combination: R1, R2 and R3. According to the law of conservation of energy, the power supplied by the voltage source will be equal to the power taken by the entire circuit, and the power taken by the entire circuit will be equal to the power consumed by R1 plus the power consumed by R2 plus the power consumed by R3. So according to the law of conservation of energy, the power supplied by the voltage source will be equal to the power taken by the entire. We can calculate the power supplied by the voltage source with the help of this particular equation. The voltage across the source multiplied by the current in the source gives you the power supplied by the voltage source. The power consumed by R1 will be equal to I1 square R1. The power consumed by R2 will be equal to I2 square R2. The power consumed by R3 will be equal to I3 square R3, as the power supplied by the source is equal to the power taken by the circuit. So the power taken by the circuit will be equal to P1 plus P2 plus P3. We will do a few numerical examples in the upcoming class.